Here's another thing I really want you guys to see. There is a way to do this, which is very complicated and very precise, what we're going to do. But what I want to prove to you is dimension analysis is awesome. It's called the Stroke Theorem. It is quite complicated if you want to do it the Newtonian way or the Lagrangian way or any of the other ways that we've learned. If you ever go into an applied field, you will require to derive it at some point in your life. But here's the beauty of dimension analysis. We can do it in 4 steps. Ready? We are going to do this. It's called velocity of a sphere through a viscous liquid. So think about a raindrop falling from the sky. A simple example, right? In order to do dimension analysis, what is the only thing I need to know? What that velocity that I'm looking for depends on. And in order to do that, I'm going to tell you one thing. So if I have a sphere and it is falling, can I write Newton's law? What is sigma f acting on it? mg and drag. What is this drag that we're talking about here? Whatever it could be. It could be air resistance, it could be other particles in its way and all of that. So that's the only term I want to worry about. Then that means whatever that drag is, the external force has to equal that in order for this thing to fall. Agreed? So the gravity has to overcome this drag. So what does this drag depend on? Do you remember when we did this before? I just gave you the minus BV. Now is the time to calculate it. What is that B? Okay, ready? This drag has to depend on certain things. And experimentally, we find that this drag depends on the radius of your sphere. It depends on the eta that you're following through, and it depends on the velocity of your fall. The faster you go, the more drag you experience. Is that true?
Yeah.
The thicker the material, the more drag you will experience. And the larger your object, the more drag you'll experience. Okay, how do we do dimensional analysis then? What will be on this side? This is a force. It will be newtons. Dimensionally, how do we write that? I'm going to write alpha, beta, gamma. What will be the dimensions of D? Okay, mass to the 1. What else?
Length of the 1.
Thank you.
Times over 2.
Proportional to L to the alpha. What was N? N was Newton seconds over meters squared. Yeah, that was it. So then that means it's kilograms meters over seconds squared seconds divided by meter squared. Or can I write this as one of the seconds go away, kilogram stays, meters, one of the meters goes away, right? Somebody quickly do the math. So it'll be kilograms
over meter seconds.
Over meter seconds. Thank you. We did that right? Okay. So dimensionally, can I write this as L to the minus 1 and T to the minus 1? And then V will be written as L T minus 1. And then I have to put betas and gammas. So beta and gamma. So I will be left with L alpha minus beta minus gamma, M beta, and T. Please make sure I don't.
Should be plus gamma for L.
Oh, yeah. We did that right? Good. Equating powers, what do we get? for M. 1 equals beta. What do we get for L? 1 equals alpha minus beta plus gamma. What do we get for T? Minus 2 equals minus beta minus gamma. So here I can calculate gamma. 2 minus 1 plus 1. Gamma equals 1. Beta equals 1. What does alpha equal? Thank you. Plug it back into equation 1. What will I get? Drag is proportional to
Resistance.
R to the 1, eta to the 1, V to the 1. Okay, do you want to know what the constant is that goes in here? No. 6.
Who gets like the square?
I know. Experimentally. That was actually 6 pi. Yeah. So drag is actually 6 pi R eta V. And that, my friends, is called the Stroke's theorem. Strokes.